In this segment, we'll look more closely at how malloc manages dynamically allocated blocks, and we'll examine what happens when you mess up the runtime heap. Our sample code here allocates two blocks of ints, one with 5 ints and one with 10. Using calloc ensures that they initially contain all zeros. So let's start by printing the starting addresses of the blocks. We do right here on line 13. And there are two sample runs actually shown at the bottom of our notes slide. And we've actually run these with different compilers. So right away there's something interesting. The locations are at different spots of those two blocks, are at different spots in different compiler runs. Each compiler comes with its own implementation of the allocation library functions like malloc, so the exact organization of the runtime heap will vary per compiler. Now, from the programmer's perspective, there's really no difference unless you examine the actual addresses, but this does drive home the point that a bug that might accidentally work under one compiler may fail under another. So, under the watcom-c run, the one up here, answer the following question. How big do you expect the first block of 5 ints to be? And do the addresses in pointers block 1 and block 2 differ by that much? So coming back from a pause there, your answer should be that the assumption, given the assumption of 4 bytes per int, that the block 1 should be 20 bytes long, but the pointers differ by 24 bytes, and we've got a diagram up here that reflects that. The actual address beginnings of the two blocks differ by 24 bytes. So apparently there's some extra space in here. And what is that extra space? It's a 4-byte value that hangs out, if you will, just before the start of the second block. Right in there. And there's another one just like it, in fact, before the first block as well. What's going on here is that all dynamically allocated blocks have headers, a few bytes that go before the address that you think of as the start of the block. When malloc allocates a block, it boosts the requested size by 4 bytes, at least in this example, and puts header information at the start of the block. And then it hands you a pointer to the byte just after the header, in effect lying to you about where the block starts. You don't realize there's extra data being carried around before the start of your block. But why does malloc do this? Consider what happens when we pass block 1 or block 2 to free. Free's job is to mark all the space in the block as reusable. But how does it know how much space there is, given only the block's starting address? We never passed any information as to the block's size. Free knows the block's size because it's stored in the header. Free and malloc are in cahoots. Malloc puts the block size into the header, and Free retrieves it. Specifically, Free reduces the address you gave it by 4 bytes to the start of the header, reads the block size from the header, and then frees that many bytes. So, question 2 then. What's going on line 14? What does indexing by -1 accomplish? Recall the earlier lecture on pointer indexing, and of course look at the output from this down on line 32. So coming back from a pause there, it returns the 4-byte headers, printing them as integers. Indexing by -1 backs up by 1 target's worth, and that's 4 bytes for an int target. So then it dereferences, and we get the contents of those headers. Apparently the headers contain 25 and 49 respectively. That's about right, but it still needs some explanation. First, malloc and calloc always allocate block sizes in multiples of 8 bytes, at least on the 64-bit architecture that these examples ran on. And that ensures that the block and the data after it fall on divisible by 8 boundaries to avoid bus errors. And the block sizes include the headers. So our two block sizes are the expected 24 bytes for block 1, 4-byte header and 20 bytes of ints, but a rounded up 48 bytes for block 2, rather than just 44. A divisible by 8 size also means that the bottom 3 bits of the size value will always be zeros. Review a little bit of binary math from prior lectures if you need to see this. So, never one to waste even a few bits. malloc and calloc use those bottom 3 bits to set true and false flags about the block. I'm honestly not sure what setting the LSB the least significant bit signifies to the WATCOM-C allocation routines, but it must mean something because the size values of 24 and 20 and 48 that we expect have actually been bumped up to 25 and 49 by setting that bottommost ones bit. So, do you need to know all this detail? No, but it is important to understand that the runtime heap is full of very delicately designed information, that the blocks you allocate are near one another, interspersed with that information, that header information, and that anything you do to mess it up will cause a catastrophe. And that's if you're lucky. So, let's cause a catastrophe. Look at lines 16 through 17. In question 3, what's wrong with those 2 lines? And what are they going to mess up? Look closely until you see the bug. Coming back from a pause there, the loop limit should have been dim 1 if we are indexing block 1. The loop will march right off the end of the first block. Now, that's an easy kind of mistake to make, you'd have to admit. So, on lines 19 through 21, we print block 2's header, and then we print block 2's content. The output down here shows the result. So question 4, what happened to the 49 that was supposed to be in the header? And I thought that calloc would set blocks to 0 values. Why does the second block have non-zero content? And coming back from a pause here, it should be pretty obvious. That's the data from the line 16 through 17 loop here. It overwrote the data in the second block, went kind of just charging right through the first block and all the way into the second. So it overwrote data in the second block, and even worse, destroyed its header. Okay, so now let's free the second block down on line 24 here. The result is the blow-up that you can see on lines 34 through 37, or if you want to see it under the GCC compiler, down here on line 43. And don't worry about what happened to the line 23 printf up here, by the way. We'll discuss that shortly. Now, your first reaction to encountering such a bug might be, why can't these compiler writers get their allocation libraries debugged properly? Why is free blowing up? But the libraries get used so heavily that all the bugs have long since been washed out of them. If malloc, calloc, or free blow up when you call them, it's because you've corrupted the runtime heap. This is a really hard bug to find, involving lots of poring over code, sometimes thousands of lines of it. Best to be careful in the first place. So, before we discuss that missing printf output from line 23, here are a few more questions to think about regarding runtime heap blocks and headers. Say I have a large array declared just as a local variable. Like that. And I'd like to contribute it to the runtime heap by freeing it. Like that. Will this work? Can I dump an extra 1,000 bytes into the runtime heap this way and have a bit more memory to allocate later on? Now, be specific. What's likely to happen and exactly why? So, coming back from a pause, the 4 bytes before the start of your array, whatever they may contain, will be used by free as the header. So free looks at that garbage data and says, like, wow, 1,487,638 bytes. That's a nice big block, and frees that space, wiping out God knows what, and corrupting memory and the runtime heap. You might not even find out about it until you do another malloc or free much later. Here's question 6, a bit of historical lore from the field. The classic Kernighan and Ritchie text famously mentions specifically this bug, freeing something not originally allocated. With what dramatic adjective do they describe it, and on what page? Look it up in your text and find out where the text discusses freeing and allocation in general. Of course, that's the real intent of the question here. Coming back from a pause, they famously term it a ghastly, that's the adjective, error on page 167 near the bottom. It's a well-known quote among C programmers. So, in closing here, let's look at that printf on line 23 that never showed up in the output. Why not? It did run, but writing output to a screen or a file is time-consuming, so printf buffers its output. It stores it in a memory block that's held in the standard I/O library until the line of output is complete. And in our example, the line 23 printf starts but does not finish an output line. Line 25 down here finishes the output line. And then the buffer from line 23 printf along with line 25's output will go to the screen. Now, normally you don't even notice this. It happens too fast. And printf's buffer is, by the way, always flushed or sent to the screen before a scanf, so that any prompts that you print will show up even if they don't end the line. The only time you really notice the buffering is in cases like ours, where the program blows up between the first and the second printfs. Printf's buffer is part of the program's memory. It's often a dynamically allocated block, in fact. So it vanishes with the rest of the program when the program blows up, and thus the first printf's output never makes it to the screen. This makes it look like the bug happened before line 23, since you never see the line 23 output, and it can be very misleading. So the lesson is, when you do a debugging printf, add a return at the end. Don't write printf got to this point, damn it. Write printf got to this point, damn it, return, and then you'll be fine.